Hello everyone, in this video I'm going to be talking about how to reduce aromatic compounds, or another way of saying Birch reductions mainly, and its mechanism. So typically if I have an aromatic compound, and I have an example of a benzene here, the Birch reduction is done in the presence of a metal, so that could be either sodium or lithium, and in the presence of liquid ammonia. Now you may wonder how you get liquid ammonia, because ammonia is a gas at room temperature, so that's why you have to run this reaction at a low temperature, and the low temperature means it could be anywhere between minus 33 to minus 80. And why minus 33? Because that's going to be the boiling point for the NH3. So if we go over minus 33, then ammonia is not going to be liquid anymore. So you got to have it in a low temperature. And in addition to that, you need some sort of alcohol, whether it's in methanol, ethanol, or in some cases, especially with lithium, you may also see tert-butyl alcohol as well. So this actually reduces this benzene here, and it will have only two double bonds left. So it will look something like this. Now you may wonder why there is a need to do the Birch reduction, and why you can't just do a regular reduction using hydrogen and some sort of catalyst like you would do in case of alkenes and alkynes. And the answer to that is it's not that easy to run that reaction. So suppose if I have this benzene, and if I want to go ahead and create an cyclohexane from here, so I'm just going to copy this down on here. So get rid of all the double bonds there, makes a cyclohexane. And if I want to do this in with the catalytic hydrogenation using nickel and hydrogen, I would have to have almost 100 atm pressure and 150 degrees Celsius. Now, temperature may not be the issue there, but getting 100 atm pressure is not going to be a joke there, so it's not practical to do. As a result, there has got to be a better way of doing these things, and that's when the Birch reduction steps in. Now, how does this really work mechanistically? Uh, Now, you may wonder, since you have a sodium and you got this methanol in there, why not the sodium deprotonates the methanol? Because sodium is indeed a strong base as well. And that usually doesn't happen because this sodium and this liquid ammonia, they combine together, and the sodium actually donates its electron, and the electron is just going to be right where the liquid ammonia is. So I can just kind of write down an electron there, and this is going to be called a solvated electron. So since it makes a solvated electron, it doesn't really deprotonate this alcohol, but instead it goes on to the aromatic ring and it does in a radical mechanism type. So once you get this solvated electron, like in this case, and obviously you got this Na plus there being made because you lost the proton electron there, then I can go ahead and grab this benzene now, and I can go ahead and bring in the electron that you just solvated. So I'm just going to go and write down the electron there. So it does a radical mechanism where this particular ring is symmetrical. It doesn't really matter which pi bond I start out with. So it's going to go ahead and do a radical mechanism where this comes down here, and this comes down here as well. So make sure, keep an eye on what type of arrow I'm making. Since you're only transferring one electron, you gotta make a half-headed arrow there, and the other electron will be coming down here onto the other side. And in the process, the other electron from the other pi bond is going to be coming in there as well to create the new pi bond there. And then the other electron from the second pi bond will go onto that carbon as a radical. So you end up making, so I'm just going to grab this benzene ring right here. So I'm going to erase a part of it. So you created new pi bond right here, and now you got a anion right there, and you got a radical right there. So this is anion radical intermediate that you create there. Okay, then in the next step, I can have this alcohol that you have selected, this can be deprotonated, so you can use this lone pair of electron to grab that proton from the alcohol. Some behaves. Yep. All right, so now you got one site reduced. So I'm not really going to draw the hydrogen. Well, I could technically. So let's suppose I already had a hydrogen here. Remember there was the one hydrogen there, so I'm going to go ahead and draw that for right here. And then now you added another one. So technically you don't really have to draw it because you don't really show the hydrogens on the skeleton structure. And then what happened to the other radical there? Because we got to put the hydrogen there as well. But before you can do that, you got to have another electron so that you can have an anion there. So another solvated electron comes in here, and it goes there, and that would create a second anion here. And then finally, you repeat the step. You have this CH3OH that you're using. So this could be a negative charge. So this is going to go grab this proton here. And this is going to go back and create this methoxide here. So that's going to go ahead and reduce that as well. So I'm going to go ahead and have a proton here. And remember, there was already a proton on that particular carbon to begin with. We didn't really draw that because that's just make it looks too busy here. So I'm going to go ahead and put the hydrogens there that was already there. And then you have another hydrogen that's just placed there. So instead of using methanol, you can probably use a methanol D, but what if you use a methanol D, then what happened? Then instead of installing the hydrogens, you would be installing the deuterium there. So like for example, if I just take this and duplicate that and come down here. So the idea is, what if I use instead of methanol, but methanol D, then I would have a deuterium here, and I would have a deuterium there. Then in that case, you got to show that deuterium because it's not automatic on the skeleton structure. If it's anything beside hydrogen, you gotta draw that out. So you could actually put the deuterium in there as well. Now, what happened if the ring is substitute? Like you got some group on it already, whether it's an electron donating or an electron withdrawing. So if you have a ring that contains an electron donating group, so you gotta memorize your electron donating groups and electron withdrawing groups. So this particular anisole here, it's got the methoxy group on it, so it's actually an electron donating group because it's got a lone pair of electron. So the idea is the product that you're actually going to make here, I'm not going to draw the mechanism here because it's going to be very similar, but I'll tell you the reasoning why it would work that way. So you will reduce this, but you would actually either make this, or you can have, double bond the other way around, which is the same thing. I'll just draw that. I'll say over here because it's the same thing technically. Don't think that they are two different things. They are both going to be the same things. So you're actually going to have the double bond right next to your electron donating group. That's how you want to memorize it. And why it works that way. So think of this, when I'm trying to add an electron here, the solid electron that you get, where would I want to add the electron? I don't want to add the electron on some of these positions like if I add the electron right here, what's going to happen? I'm going to have an electron right next to an oxygen atom that already has an electron. So another way of saying, I'm putting an electron on the carbon that has an electron donating group attached to it. So it's actually going to destabilize it. So you can't put it right there, and I cannot put it on the ortho position as well, because if I put it on the ortho position, eventually it's going to create either the radical or the anion on that carbon, and I cannot do that on the para position either. So the only place that it can really go would be your meta position. So this is going to be the place of attack there. All right, and then you can kind of draw this out. So, okay, I'm going to have the radical here, and this comes down here, this comes down here, and then I'm going to have this negative charge created there. So this is how it's going to look like mechanistically. So you will end up making, I'm just going to copy this down. So remember, we didn't really touch this double bond, so that's already there. And then we created the anion here, and then we created the new double bond right there by this relocation there, and then we got the radical right there. So this is what is going to be created, and then you can follow the rest of the mechanism. So you can see whenever you have electron donating group, the site that's bearing the electron donating group is not going to get reduced, but rather it's going to have the double bond on it. So since you have these electrons being poured into the ring, and if you have an electron donating group attached to it, they actually deactivate the ring for the Birch reductions. Remember, it's not the same as the electrophilic aromatic substitutions. It's the Birch reduction where you're actually pouring in the electrons into the ring. So if you have an electron donating group attached to it, it's going to deactivate the ring, but it's going to be toward Birch reduction. So a lot of times when the ring is deactivated, you may see people using lithium with liquid ammonia, obviously, and instead of using methanol, they may be using tert-butyl alcohol in that particular case. Uh, but if you have an electron withdrawing group, it actually better for the ring because it's making the ring electron deficient, so it's going to be easier to add an electron radical onto the ring. So electron withdrawing groups makes the ring faster toward the Birch reduction. So when you have that, you will be actually reducing the site that actually has the electron withdrawing group attached. So instead, you're going to have the double bonds on the other position. So make sure you know the regioselectivity, where to place the double bonds when you reduce by when the ring has either the electron donating group or electron withdrawing groups. So the idea here is I actually wanna go ahead and add electron onto that particular site. So I can go ahead and actually add this electron right here, and then this comes down here, and this comes up here, this comes up here, and then this comes down here. And it's not only that position. If you pick some other positions, and I'll show you which ones, you will get similar results. So we will be having a new double bond right there and creating the anion right there and the radical right there. So this is a very stable structure because the negative charge is right next to an electron withdrawing group. So whenever you have an electron withdrawing group, you can have the solvated electron attacking the ortho and even the para positions. And including you can also attack the site that actually having the electron withdrawing group. But when you have an electron donating group, you actually want to have this electron added onto the meta position. So I'm going to say the meta right there. And then eventually you can follow the rest of the mechanism. It's going to be very similar to what we did on the top, but make sure you know the regioselectivity when you're doing these Birch reductions. So once you have these two double bonds in the ring, you can easily reduce those by using catalytic hydrogenation. And in that case, you don't have to use very harsh conditions. A couple of atmospheres, maybe 50, 60 degrees Celsius temperature should be good enough, just like an alkene. If you have any questions on this, feel free to leave any comments in the section below.